In this video, I want to quickly introduce the relationship between the electric potential and the electric potential energy. So if you remember in the map of things, these are these two things. The electric potential is V, that's the thing we were just talking about. And then the electric potential energy, which is similar to all kinds of potential energies that you've studied before, it's about the interaction between charges. Where the electric potential was about the influence at some location in space due to some charge, I have to think about when I think about the electric potential energy, I say, there's some charge that is sitting in a potential and it wants to move between 2 points, just like we did in gravity, for example, when we said, suppose I have 2 points here that have different heights, a roller coaster or somebody rolling down the mountain or something like that. And then there are 2 points, P1 and P2. And I want to think about moving, in this case, when I'm thinking about gravity, I'm thinking about a mass that is moving between them. When I think about electricity, I think about a charge, which is the analogous thing to the mass when I'm thinking about gravity. Now, suppose I have a mass that starts out at point P1 and then it ends at point P2. I can talk about the change in the gravitational potential energy as being mgy2, so that the gravitational potential energy at the final situation minus the gravitational potential energy at the initial situation. And I could also always write it like this because the mass is a common factor. I can take it out. So this is the mass of the object being displaced in the landscape that is defined by the other objects. So in this case, this one, the difference between the gravitational potential at the 2 points is due to Earth itself. This little g comes from Earth. That's the gravitational acceleration due to Earth. So gy2 and gy1, these are called the gravitational potential at points P2 and P1. When I multiply them by the mass, they become the gravitational potential energy. So the analogy then is that if I want to move a charge between 2 points, I want to move a charge Q naught, let's say, it starts out at point P1, and I want to move it to charge P2. Question is, what is the change in electric potential energy as this charge is transferred from point 1 to point 2? Then I can talk about the charge multiplied by the difference in potential, or the electric potential difference, or the voltage between points P1 and P2. So the amount of net charge being transferred, Q naught, is moving in a landscape that is dictated by all of the other charges around. So this is set up by some other charges, and then I have the charge Q naught moving in that potential landscape between these 2 points. So I can always calculate the amount of change in the electric potential energy as charge Q naught moves between points P1 and P2 as the net charge being transferred, positive, negative, right? I have to put it with its sign because, again, the electric potential energy is a scalar quantity. So positive and negative means more energy or less energy. And Q naught is the amount of net charge being transferred, could be positive or negative. That wasn't the case for the mass. The mass was always positive, but Q naught could be positive or negative. And of course, the potential difference could be positive or negative. So I could be changing the energy positively, adding to the energy, or I could be subtracting from the energy, taking away energy by moving the charge from one location to the next. Of course, the SI units for energy is joules. If you put the charge in coulombs and you put the electric potential in volts, then that's coulombs times volts. And remember, volt is joules per coulomb, so the coulombs cancel and I'm left with joules. So that'll be the unit of energy.